In this video, I'm going to work through how we came up with Snell's law. Snell's law is the relationship between the angle of incidence and the angle of refraction when a wave moves from one medium to another medium. So again, imagine some sort of barrier. This could be air, and this could be glass, or this could be like deep water, and this could be shallow water. It doesn't really matter. The wave comes in at some direction. We compare that direction to the normal, and we call that theta I, or the angle of incidence. Because here air has a refractive index of 1 and glass has a refractive index of 1.5, we know that this ray or this light is going to have to slow down, and when it slows down it goes closer to the normal, and so it's going to come out at theta r, or the angle of refraction. We also know that this relationship is n1 sine theta 1 equals n2 sine theta 2, or n of the incident material, sine theta incident material, is equal to n of the refractive material times the sine theta of the refractive material. What we're going to do in this video is we're going to prove that equation. To do that, I'm going to change instead, well, that was a really bad line. Instead of looking at the, that's not what I want to do, I want to draw. Instead of looking at this as a, ooh, that's really thick, how do I make that thinner? Well, that didn't help. Okay, whatever. Instead of looking at this using a ray diagram like I did up here, I'm going to do this using a wave front diagram. I'm going to use red to do my incident waves, so they're going to come in like this. Just a second, see if I can move that guy a little bit so he's in line. There we go. I'm going to change this one too. So I'm trying to draw all these as parallel as I can here. So those are my wave fronts coming in, and then I'm going to say, just for the sake of argument, that this is going to be, let's make this deep, and I'll make this side shallow, which means that when these waves move from one region to the other, they're going to end up with a shorter wavelength, or they're going to end up closer together. Also note that if a crest is at this location right here, that when I start to generate a wave in this medium, I also have to have a crest at that same location. So here are my refracted wave fronts. Nah, I don't like that at all. Let me try that again. First of all, I gotta get those guys to meet up, and then I gotta go parallel, just like that. Okay, so what I can see here is that my wavelength in my deep water is larger than my wavelength in my shallow water. Now, to figure out my angles and how all this is related to sine theta 1 and sine theta 2, I'm going to use two triangles right here that are both related to this common length in the middle right here. So if this ray is coming in with an angle theta here, then this angle right here must be 90 minus theta. And if that angle's 90 minus theta and that angle's 90, then this angle right here must be theta degrees. One more time. My ray, that's what this dotted line here represents. Here, let's zoom in here. My ray coming in comparison to my normal, is what I call my angle of incidence. If that angle is theta, and this is 90 degrees, then this angle right here, I'll call him alpha. Alpha has to be 90 minus theta. So that's 90 minus theta. And then if I consider this entire triangle, oh, what did I do there? Sorry, I consider this entire triangle, and I can try and find this angle right here. Oh, crud. Let's see if I can put that barrier back on. Close enough. Okay. If I can try and find this angle right here, if this whole triangle adds up to 180, that's going to be equal to 90. That's this guy right here, the right angle, plus alpha, plus this other angle. I'll call him beta for now. And so that's 90 equals, bring that over, alpha is equal to 90 minus theta plus beta. And then obviously these 90s can cancel, and I can see that theta and beta are the same. And so I can get rid of this guy here, and I can recognize that that angle is also equal to my angle of incidence. I can do the same thing starting over here. Again, oh, I should do that as a dotted line, not a solid line. This is my ray coming out. This is my normal. So this right here represents my angle of refraction. This would be 90 minus my angle of refraction. This is 90 degrees, and by the same reasoning then, this right here is equal to my angle of refraction. Now let's move over here so that we have some space to work with. What we're saying then is that this distance starting here and ending here is common. So I'm going to call that distance d, and I'm going to say d equals d. Now in this triangle, that d is the hypotenuse. So sine theta I, that's this guy here, is going to be equal to the opposite over the hypotenuse. Now sine theta I is equal to, I just said the hypotenuse we're going to call d, because we recognize that it's common between the two things, so that's what we're going to call it. And this opposite side is the distance between successive crests, which earlier I said was the wavelength. Now I should be careful here, this is the wavelength in the incident medium. Similarly, using this triangle, recognizing that this is the opposite, and this is the hypotenuse. Careful here, that is the hypotenuse, this is the adjacent over here. I can say that the sine for my theta r is equal to my wavelength in my refracted medium divided by my distance. Same thing. This is my wavelength, right, in my refracted medium. This is the common distance, so that's my sine ratio. Now I can solve both of these equations for d. I'm going to bring d up here and bring the sine down. So d equals sine, or oops, try that again. D equals lambda I divided by sine theta I. And d equals lambda r divided by sine theta r. Moving that over, set the two things equal to each other. Lambda I is equal to sine theta I. Lambda r is equal to sine theta r. And now we just have a little bit of math to finish off this proof. First of all, recall that changes in speed have to be done by the wavelength. So the wavelength is equal to the wavelength in free space divided by the refractive index. So theta I, or lambda I, for example, would be equal to lambda naught divided by the refractive index in I, and that can be done for the refractive index or the wavelength in the refracted medium as well. So I'm going to change this to lambda naught over ni over sine theta I, and lambda naught nr over sine theta r. Now these guys are both the same, so I can divide out, assuming that they're not 0, and I'll get 1 here. and then I can bring my sine theta, and then I can take this guy on the bottom and invert and multiply, I guess. So 1 on ni times 1 on sine theta I is equal to 1 on nr and 1 on sine theta r. So 1 on ni sine theta I is equal to 1 on nr sine theta r. And then I can just reciprocal these things. Ni sine theta I is equal to nr sine theta r. And that's it. That's Snell's law. So by drawing the wavefronts, recognizing that a location of a crest has to lead to a location of another crest, changing the wavelength to represent the change in speed, as done here, and recognize that they have this common distance. If I consider these two triangles, I can show that the new angle based on I can show the relationship between the new angle of refraction based on the angle of incidence has to follow this pattern simply to allow the wavelength to be adjusted the way that we needed the wavelength to be adjusted. So that's what Snell's law is based on.